What is an earthquake? What causes an earthquake? Why can't we predict them? Although we still can't predict earthquakes, we have learned much about them as well as the earth itself. We have learned how to pinpoint locations of earthquakes, how to measure their size, and how to build flexible structures that can withstand the strong shaking produced by the earthquakes. An earthquake is sudden shaking of the crust caused by abrupt release of strain that has slowly accumulated in rock. When stress is applied slowly and continuously over time, most rocks will deform elastically. That is, they will rebound back to their original shape if the stress is removed or when the rock fractures. When a rock breaks or a fault abruptly ruptures, it releases strain in form of an energy called seismic waves, which radiate through Earth's interior and along its surface. Seismic waves cause the shaking of an earthquake. Most earthquakes are associated with the rupture of a fault, but they may also result from volcanic action, landslides, or any other rapid release of energy that shakes the ground. Today, much of our understanding of Earth's geology is explained by the remarkable theory of plate tectonics. We live on the surface of a planet that is actively shaped by plate tectonics. Mountain ranges, oceans, continents, islands, and other features can all be explained in part by the movement of massive lithospheric plates. There are 12 major plates and several smaller ones. In 1969, a map showing the locations of earthquakes that happened from 1961 to 1967 was published. This map is now used as evidence in support of the theory of tectonic plates. Most earthquakes occur at plate boundaries, but interplate seismicity is also common. Most interplate earthquakes are caused by volcanic activity, such as in Yellowstone National Park or the Big Island Volcano National Park. Earthquakes occur in 4 different settings: interplate settings, divergent settings, convergent margins, and transform settings. It is possible to predict where earthquakes are likely to happen on a worldwide basis. It is not possible to determine when it will happen. Divergent seismicity. The narrow earthquake belt extending along the world's mid-ocean ridges provides direct support for the concept of seafloor spreading. Because the lithosphere is thin and weak at divergent boundaries and large amount of strain cannot accumulate, seismic activities tend to be low to moderate energy and to occur at shallow depths. Volcanic activity along the axis of the ridges is associated with this type of seismicity. Strike-slip faulting is also a source of seismicity at spreading centers, when crustal slippage occurs along the transform boundaries found on most mid-ocean ridges. Convergent seismicity. Earth's largest and most active seismicity occurs at convergent boundaries, where one plate subducts beneath another in a zone of accumulating compressive stress. These regions of plate interaction are characterized by progressively deeper earthquakes along a line proceeding from the trench across the overriding plate. Transform seismicity. Tectonic boundaries may be characterized by strike-slip faulting, in which 2 plates slip past each other at a transform margin. At transforms, earthquakes are shallow, running only as deep as 25 kilometers. 2 excellent but dangerous examples of transform seismicity are found at the San Andreas Fault in California and the North Anatolian Fault in Turkey. Both are right lateral strike-slip faults.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with one foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Bilham keeps track of these changes with his creep meter, a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people, but further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
Scientists cannot predict when an earthquake will happen, but it is possible to define areas that are especially vulnerable to earthquake hazards. Ground shaking caused by earthquakes actually poses little direct danger to a person. An earthquake cannot shake you to death. However, shaking produces effects that can cause damage and loss of life. Sediment liquefaction occurs when shaking causes groundwater to rise to the surface and mix with sandy or muddy soil. The sediment loses strength, and any buildings and roads on the sediment will be destroyed as they sink into the wet, soupy quicksand. Ground shaking can cause steep hillsides to collapse. This process is known as mass wasting. It is extremely common when it is triggered by ground shaking. Fires following an earthquake started by broken gas lines and power lines or tipped over wood or coal stoves can be a serious problem. Often water lines and emergency equipment are damaged during an earthquake, and roads are made impassable, rendering it impossible for firefighters and other emergency personnel to do their work. If an earthquake generates a tsunami, coastal damage can be deadly and widespread. A tsunami is what most people call a tidal wave, but it has nothing to do with the tides on the ocean. Any movement of the seafloor, such as undersea landslide or a submarine volcanic explosion, can produce a tsunami, but the most common cause is faulting associated with an earthquake that violently shifts the seafloor and displaces the overlying water column, causing a wave. Tsunamis are imperceptible in the open ocean, but when they run aground, they may flood across the shoreline for many minutes and cause extensive inundation. Earthquakes release energy in the form of seismic waves that travel outward from the focus through the crust into the Earth's interior. There are 4 kinds of seismic waves, and they all move in different ways. Earthquakes radiate seismic energy in the form of 2 types of surface waves, love waves and Rayleigh waves, and 2 types of body waves, primary waves or P waves and secondary waves or S waves. Body waves travel through Earth's inner layers, but most of the energy in surface waves moves along the planet's surface. Because earthquakes cause such terrible destruction, people have been trying for centuries to measure them and understand how they work. Today, geologists are able to use instruments that measure and record the vibrations produced by earthquakes. Seismometers can detect, record, and measure the arrival of surface waves and body waves. Using these measurements, scientists can determine the location of an earthquake epicenter, the depth of its focus, time of occurrence, and type of faulting, and estimate how much energy the earthquake released. These instruments are called seismometers. They use highly precise electronic signals to measure seismic energy. Even though today's technology is so advanced, we still cannot predict earthquakes. Due to history, we're able to tell where an earthquake is more likely to happen, which can help residents of those areas be prepared and learn about the hazards. However, knowing when and how strong it will be is still a mystery.